Okay, good morning. Welcome to
FamilyMath number 925.
FamilyMath925. So this is a computer program that Francis Sue shared yesterday. And it's about something called scissors congruence, or the Wallace-Bolyai-Gurwine theorem. Tell me about what this program's doing.
Well, it's making two polygons that just have to be polygons, like they can't intersect each other, so you can make them like bend in, you can make them like all these really crazy shapes, they just can't cross like that.
Okay.
So I'll do that, and then we make two of them. And see that? So then when I click this, it'll just scale them so that they have the same area. And then it'll chop the green one up and then fit it so that it puts it in the orange one. And you can see it chopping it up. And this is called scissor congruence, apparently.
Alright, so this is a pretty complicated example to start, but that's fine.
But basically, I'll wait till it's finished.
Okay.
Yeah, and apparently you can do this with any two polygons, as long as they have finite numbers of sides.
Alright, nice. So,
So, I don't know if you can see it on here, but it divides it up into, I think, all triangles, and then the triangles go down here and you make them into rectangles. And then those rectangles you make into different triangles and you put them on there.
okay. Why don't you show us a slightly more simple example and then talk about what you're seeing as it plays out.
Alright, I'll do like that. First one, maybe that for the second one.
Okay. Alright, so what do you expect to see here?
So we just chop it up we make triangles here, chop them up into rectangles, and then re-chop these rectangles into new triangles, although they're not always the same rectangles because I did split it.
Okay.
And then, so you basically need to see how many triangles you need to chop each shape into.
Okay, so each shape itself gets chopped into triangles.
Mm-hmm.
And then what happens to those triangles?
And those triangles, I think I'm not sure if it's necessary, but for the purpose of the demonstration, the triangles are made into rectangles.
Okay.
And then all the rectangles make one big rectangle here. And then that big rectangle is re-split. And then those smaller bits are remade into triangles.
Okay, so I think there's a replay button here. Okay, so here we go. So there's your triangle, and it's folded up into a rectangle in a pretty interesting way.
And then the rectangle's redivided.
And then unfolded into those triangles.
Different triangles.
Okay. So are you surprised that this theorem is true? That if you take two, fairly nice polygons, finite number of sides, no intersecting sides, or no crossings, I guess, that you can cut them up and reassemble them?
It seems like a pretty natural thing that could occur because they've got the same area and they're pretty simple shapes.
Okay.
So intuitively you would think this would be true, but if you gave me if you gave me these two shapes and told me to chop them up into triangles and put this shape into that shape, I don't think that I would be able to do it without seeing it first. Okay,
yeah, so actually one of the things I was going to do is have you do a square and do an equilateral triangle. But then I thought maybe that was just going to take the whole morning to figure out how to do. But what do you think would happen if you do a square and then an equilateral triangle? So your green shape is a square, the left shape is a square, and the right shape is an equilateral triangle. What do you think is going to happen?
Well, I think you might get something similar to this. The square might be chopped up into two triangles, and then those triangles, you might not even need to chop it up. You could just chop it up so it fits into the triangle. Because here you chop it up and then put it together into a rectangle, but you already have that rectangle, so you wouldn't need to do that step.
Oh, interesting. Okay. So yeah. So actually the interesting question is there something special about that rectangle that it's being chopped up into? So what do you think? If you drew a square and equilateral triangle, do you think it's going to just, since you are starting with a rectangle, do you think it's going to stay, or do you think it's going to be chopped into two triangles?
It'll probably be chopped and put into something slightly different.
Okay, well, draw it out. Let's see.
Alright, I will. What's the? Right. I have to let this one play out first.
Okay, yeah, that's fine.
Okay. I will try to get as close to a square as I can.
Yeah, I mean, just do your best. It doesn't have to be perfect.
That's pretty close. And here's an equilateral triangle. Alright. See, it's chopped, and then I'm gonna make it into, I guess, almost exactly the same, but it's slightly different. And then that one didn't even need to be chopped into multiple different rectangles. It just took that rectangle.
Yeah. Why do you think it did that? Why do you think it went right from that second rectangle right into the triangle?
Well, because I think you can just do that. I mean, it has it kind of over there. Like, you can take a rectangle and then make it into a triangle. You don't, and plus there's only one triangle. You need to chop it up.
Okay. Neat. Do you think you could do this in 3 dimensions?
If you had the same constraints, I think you probably could. Like, it doesn't intersect itself, and there's a finite number of sides. I think you probably could. Might be a bit harder to visualize, though.
Yeah, the 3-dimensional problem was regarded as a much more difficult problem. In fact, in the beginning of the 1900s, there was a mathematician named David Hilbert who proposed a list of sort of important mathematical problems to be solved, and that was one of them. I think it was actually the first one to be solved, but it was definitely one of them. Could you do the scissors congruence in 3 dimensions? And the surprise was, it turned out the answer was no.
Huh, so it doesn't always work.
It doesn't always work in 3 dimensions. So you can make 2 shapes, and the mathematician's name was Den. I may not be pronouncing that right, but I think it was Dehn. Proved that there existed 2 relatively simple shapes that couldn't be scissor cut and reassembled in 3 dimensions. So there's something special about 2 dimensions here. So this is it's a pretty cool fact. Did you find any like really neat examples that kind of surprised you?
Not really. I was mostly trying just to break it, like make really convoluted shapes and see if I could do it. And I always was able to do it.
Okay, cool. Yeah, it's a neat program. This program won an award for the best mathematical visualization of 2018 or something. So it's cool. It's a really neat program. All right, good job, huh?